17 topics, electrochemistry.
It is an error.
You don't need one. No, don't need one. You just walk through the water. There's an error on the electronic version of it, so nobody can do it. So I don't want to process 160 of it. We'll probably do like 120 of it. All right, so if you have somebody who sits next to you in the next like 2 or 3 minutes, tell them we did not have any class assignment. And you're not lying to me. All right. Exam 4 is coming up on the 28th. That is 2 weeks from tomorrow. Again, it will be lean heavily upon electrochemistry. We'll have the temperature units of the rate constant, of the equilibrium constant from what we covered last time, and we will have a little bit of nuclear chemistry. I still do not know exactly how much nuclear chemistry there will be on. Okay, last time. No in-class assignments today. I can tell who walks in late. I might take it off. Might there be an error? Okay. Technology is wonderful, but don't rely on it. All right, so last time we reviewed what is a redox reaction. Redox reaction is an oxidation reduction reaction. You cannot have one without the other because ultimately it is nothing more than an electron transfer reaction. You have to have something that is the source of the electron. You have to have an electron donor and you have to have an electron acceptor. Just like we had to have a proton donor and a proton acceptor for acid-base. But now we're talking about electrons. So something is going to be oxidized, something is going to be reduced. I think this chapter probably has more mnemonic devices in it than any other chapter. Oil, oxidation is the loss of electrons. Rig, reduction is the gain of electrons. If you don't like that one, there's another one called Leo-Line-Filter. I don't care which one you use, as long as you are able to tell me what's being oxidized and what's being reduced. All right. Balancing redox reactions, you don't need to write this down because I've got this exact same set of instructions on the PDF that I posted this morning. Balancing redox reactions is the name of that one. I sent you a link through an e-learning announcement. So first step, we need to assign oxidation numbers and determine what is being oxidized and what's being reduced. All right. Second, we need to separate the reactions into half reactions. All right. One for oxidation, one for reduction. Then we need to balance each of the half reactions with respect to mass. We have to do this in a specific order. First, we balance everything other than H and O. And the reason why is because H and O can ultimately be given to us through the solvent, water. This is always true in aqueous solvent. And everything we're going to deal with is aqueous. All right. Balance everything but H and O. Balance the O by adding water. We can add solvent to a reaction, no problem. Then we're going to balance all the H's in the reaction by adding protons. Okay? Doesn't matter whether we're in acidic or basic condition, we're going to add protons. Right. Then the last step, if we're in basic conditions, obviously we're going to have more hydroxide than we are hydronium. Therefore, we're going to neutralize all of the hydronium by adding hydroxide. But we have to add it to both sides of the reaction. Remember, if you do the same thing to both sides of an equation, you're not really doing anything, right? In this case, we're not doing anything because the H and the O is already balanced. All we're doing now is we're neutralizing all the excess acid by adding hydroxide. All right, now, when I add enough hydroxide to neutralize all of the hydronium, I'm going to make a bunch of water. So I need to adjust my waters on both sides. Last step is to balance charge by adding electrons to whichever side of the reaction it needs to be added to. One, we'll have the electrons added as a product. That's the oxidation half reaction because oxidation is the loss of electrons. If I'm losing something, it's on the product side. The other electrons will go on the reaction side. That's what's being reduced because reduction is the gain of electrons. Right? After I have everything balanced now, I'm going to make the number of electrons the same on both sides by finding the least common multiple number of electrons. I multiply both equations by the necessary multiple, and then I'm finally going to add the two half reactions back together again. All right. And then, of course, the last step is to check. All right. These set of 7 steps will never fail you. Okay? I know it's different than what's in the textbook. That's the reason why I put it here. That's the reason why I gave it to you as a handout. That's why if you're in my lab class, I give you the exact same handout. Because I think this is the best way to balance redox. It's the same set of instructions for every condition, whether it be acidic or basic. It also works for simple redox reactions, which we showed you last time. Right? The simple redox reactions are the ones that we balanced last semester in Gen Chem 1. Okay, so balancing the not so simple redox reactions. Let's do it. Let's work through one of these for an acidic condition, an acidic solution. Okay. We have iron 2 plus permanganate to give me iron 3 plus manganese 2 plus. My first step is to assign oxidation numbers to all my atoms and identify the substances being oxidized and reduced. Well, iron, I'm going to have iron 2 plus and iron 3 plus. If I have a single ion, okay, single ion always has an oxidation number equal to its electric charge. So iron has a 2 plus oxidation number on the reactant side, it has a 3 plus oxidation number on the product side. What about permanganate? I'm going to leave off the phases for right now. What about permanganate? It's not quite so simple. I have to actually calculate it. Okay, well, it's fairly easy to calculate. For oxidation numbers, the more electronegative elements get all the electrons. Okay? Get all the electrons. All right, so what I'm going to do is, the rule for oxygen is oxygen, when it's bound to itself, is 0. When it's bound to fluorine, it's going to be, well, fluorine is going to be -1, so oxygen should be positive, just depends. But if it's bound to pretty much anything else, oxygen is always going to be -2 for its oxidation. So what I'm going to do is I'm going to solve a little equation here. I'm going to let X be the oxidation number on my manganese. To that, I am going to add 4 times the oxidation number on oxygen. Since oxygen is the more electronegative element here, oxygen is not bound to itself. In other words, it's not in O2 and it's not in a peroxide or a superoxide. Oxygen has to have an oxidation number of -2. And the overall sum of all my oxidation numbers has to be the overall charge on my polyatomic ion. Meaning, I have to have the total oxidation numbers has to give me -1. All right? So, I have X -8 is equal to -1. X is equal to +7. Meaning the oxidation number on my manganese is 7 plus. The manganese in the permanganate ion. Okay? Now, so I've assigned oxidation numbers to everything. Now I need to identify what's being oxidized and what's being reduced. All right? So, what is being oxidized? Remember, oxidation is the loss of electrons. What is losing electrons? Iron. I'm going from 2 plus to 3 plus. Only way that can happen is if the iron loses an electron. All right, so what's being reduced? What's being reduced? Is it the permanganate or is it the manganese that's being reduced? It's the manganese that's being reduced. Okay, the manganese is going from 7 plus to 2 plus. I don't know what's going on with the oxygen. In fact, it's probably going to find its way to the salt. Okay, I don't know what's going on with it, but it's not permanganate that's being reduced. It's manganese that's being reduced. Now, permanganate happens to be a very strong reducing agent. It's got a very pretty Tarleton purple color to it. Tarleton is where I did my undergrad. Very pretty purple color, and it will bleach pretty much anything, including your skin. All right. I remember as an undergrad I did a quant lab where we used potassium permanganate as our titrant. You got it on you, you were going to have stains on your clothes. Okay, so iron is being oxidized and manganese is being reduced. I need to separate this into my two half reactions, one for oxidation and one for reduction. The oxidation half reaction is just what's going on with the iron. Okay? The reduction half reaction is what's going on with the manganese. Now, because manganese is bound to oxygen in the permanganate polyatomic ion, I have to write it this way. Okay, so that's step 1 and step 2. Step 3 is balance everything with respect to mass except for H and O. Well, we're not going to do much with the iron, are we? It's already balanced. We're not going to do much with the manganese, are we? It's already balanced. Okay? It's already balanced. It's already balanced. Sometimes that happens, and you're lucky. Next step is to balance the oxygens by adding water, since this is an aqueous solvent. All right. So, iron. We have iron and iron. We have no O present in the oxidation half reaction. Therefore, we are going to do nothing. But we have oxygen present in the reduction half reaction. In fact, we have 4 oxygens over here. So what we need to do is we need to add 4 waters to the product side. Okay? So our oxygens are now balanced. Now we need to balance any H present by adding hydronium, or protons, H+. Well, we have no H's in the oxidation half reaction, so again, we're going to do nothing. But for the reduction half reaction, since we had that water, we now have 4 times 2, we have 8 protons on the product side. Meaning I have to add 8 protons to the reactant side for the reduction half reaction. Alright? So we are in acidic conditions. We're now balanced with respect to mass. We don't have to do step 3, part 4, which would be balanced with add hydroxide. We can't add hydroxide because this is acidic conditions. So the next thing we have to do is we have to balance by charge. Okay? Now, when we're balancing by charge, here's your clue. Oxidation is the loss of electrons. Therefore, I'm going to have to add electrons to the product side for my oxidation half reaction. Right? So I have a 2 plus and a 3 plus. What do I need to add to the product side for the oxidation half reaction? Add 1 electron. Now, what about the reduction half reaction? This one's a little bit more complicated. I have a total of a 2 plus charge on my product side. On the reactant side, I have 8 plus plus 1 minus, means I have 7 plus. How many electrons do I need to add? 5. All right. So I had 5 reacting electrons to the reduction half reaction. I added the 1 to the product side of the oxidation half reaction. All right. Step 4. Now we're balanced with respect to everything. Now I need to balance both reactions with respect to one another. They make the number of electrons the same in each half reaction by finding the least common multiple of electrons. What's the least common multiple of 1 and 5? 5. So I need 5 electrons on both sides of both half reactions. Actually, let me back up. I need 5 electrons to be produced in the oxidation half reaction, and I need 5 electrons to be consumed in the reduction half reaction. Right, so the only way to get the oxidation half reaction to have 5 electrons is to multiply the entire chemical equation by 5. And again, for the reduction, I do nothing. It's balanced. Okay. Now, step 6, add the 2 half reactions together. Okay, well, I pull the 5 all the way through the equation up there. I'm going to have 5 iron 2 to give me 5 iron 3 plus 5 electrons. Add that to my other equation, which is 8 protons, 1 permanganate, 5 electrons, 1 manganese, and 4 waters. Add those together and notice that the electrons cancel on both sides. Okay? Be careful, make sure that you cancel anything that appears on both sides. Right? It may not just be electrons, especially when we're dealing with basic conditions. I add everything together, the electrons cancel. 5 irons, 8 protons, 1 permanganate to give me 5 irons, 1 manganese, and 4 waters. Check to make sure that's balanced. Check to make sure that it's balanced for mass and for charge. 5 iron, 5 iron. 8 H's, 4 times 2, 8 H's. 1 manganese, 4 oxygens, 4 times 1, 4 oxygens. Mass is balanced. Check charge. Okay, 5 times 2 plus is a 10 plus. 8 times 1 is 8 plus. So now we have 18 plus minus 1. We need plus 17 on the other side to be balanced. 5 times 3 is 15. Plus 2, 17. Charges are balanced on both sides. Right? So we have, in fact, balanced a redox reaction. All right? Okay, so that's acidic conditions. Try one yourself. Because you're going to have one on the exam in 2 weeks, so might as well knock it out, right? Balanced falling reaction and acidic solutions. Go. Work together. Make noise. Talk. Have fun. It's Monday. You've got 9 lectures left. You're not excited by that?
Not really.
You'll be excited when it's 1 month, right?
I've got so much school. My God.
Follow the steps on the lecture notes. Assign oxidation numbers. Figure out what's being oxidized, what's being reduced. Split into half reactions. Balance with respect to mass, balancing everything but O and H first. Then balance O by adding water. Balance H by adding protons. We're in acidic conditions, so we're done. Balance charges by adding electrons. Make the number of electrons the same. Add. Check.
Okay, I think I got it. Probably wrong though.
Should you get 4H plus plus the H plus 2 and 2 to the 2 and 2 and 1 H2?
Plus C into 1. Yeah, I got that. Yeah. Yeah, that's what I got.
Okay. So this is right.
Yeah, I guess so.
Did you, okay, well, kind of stuff.
1% right, but 1-2.
So, what is being reduced is NO3 and NO2, right? But I don't know if it's like individually the N only or the whole.
This is the overall
Yes.
one, so that's gonna be when you set up your equation. Oh, he's gonna work it out.
Don't worry about it.
Yeah, work it out. I'll give you time.
That ditch for it.
No, you have to try.
So tempting. I know. I'm not going to. I should have been.
Yeah. I mean, you cannot study if you want to. You can just go and test
Going
to see how much you pay attention in class, to see how much you would do just without studying.
Is that another 100?
Yeah. Like, okay, it's just me and my brain. Let's see how I do.
Okay. Exam
You
for
know
2
what?
weeks?
That is, I can't believe that you didn't get it on the same.
Oh, so
It was so simple.
that's what I told you about. That's why.
And then on this one, because I would think, if I were to get 100, I would think it would have been on the second exam. If I would have made
I thought the second exam was hard.
really, I thought it was so easy.
I thought the third exam was easy.
So is this the
I don't know. To each their own, I guess.
Yeah.
here? It's the
So do like what you're good at, remember? Like, I love doing nice tables. I could do them all day.
Nope. To be honest, I didn't even use an ice table. I just memorized how the formula looked.
If
It
it's
would
2
all-
of them, if it's 4x cubed.
Yeah, it'd be just like x squared over molarity minus x. You just multiply the molarity times k and kb, take the square root of it, take the negative log.
So you
I
didn't even
never,
have to do it nice.
I didn't write it in ice tables. But then again, I would have been smarter, but why not?
Great. If you get the answer right, it doesn't matter how you get it. As long as it's right.
Yeah. OCHEM's gonna suck. Next semester. It's not even next year
It's
anymore.
like fall.
It's like 6 months.
Yeah.
Less than 6 months. I'm going to school year round now. What the heck?
Like, you take winter terms too?
College didn't offer winter terms. I would have, but
Hi, Jen.
how are you?
What are you taking in the summer? Good.
During the summer? Oh,
You're wearing your
every-
retainer, so
Yeah,
proud of you.
I don't have gum. Like, did I tell you? If I have gum, I chew gum. If I don't, I need something in my mouth, so I use my retainer.
Well, you need to wear it anyway, otherwise your teeth will move.
I guess so, but I'm taking a lot of classes doing something.
What are you taking?
I'm taking both my governments. I'm taking micro and macro econ. I'm taking.
No
maybe
life for
physics.
you.
Yeah.
Here at UTD?
No, at Collin, because it's a lot easier. I don't want to drive 20 minutes every day and stay
Yeah,
out
from
3
Allen.
hours a day. That's not going to fly with me.
Right.
If it's online, I don't have the motivation to do it. I don't have the self-discipline to sit in front of a computer.
Yes, you do.
I don't. I really don't.
I like them. Well, some of them.
I hate all my classes. Hey, we got it
Okay,
right.
so everyone got the answer out on the board, right?
Yeah.
Yay, good. All right. A lot easier when you're working with the set of instructions in front of you than it is trying to remember it. Keep that in the back of your mind when you're practicing the homework problems, because you will have one of these to do on your exam. Okay? And I guarantee you, if you don't follow these steps, you will find an answer on there. We're good like that. All right? You should know that by now. All right? So, you just follow the steps. Figure out what's being oxidized and reduced. Copper is going from 0 to 2 plus. Copper is going to be losing electrons. This is your oxidation half reaction. That means this is your reduction half reaction. Nitrogen here. Oxygen is 2 minus, so I have 4 minus. That means this nitrogen is a 4 plus. Oxidation number. This oxygen is still 2 minus. 2 minus times 3 is a minus 6. I have a net minus 1, meaning this nitrogen is a 5 plus charge state. Oxidation. All right. balance everything with respect to, well, balance mass. Balance everything other than H and O. One in, one copper. Add water to balance oxygens. I have 3 oxygens here too, so I need 1 water over here. Balance with respect to H's. I added 2 H's. I have to add 2 H's here. Balance with respect to charge. This is the rate oxidation, meaning the electrons have to be lost. They have to be on the product side. 0 to 2 plus means I need 2 more electrons. This half reaction, 2 plus minus 1 is a plus 1. There's nothing over here. All I can do is add electrons. So I balance that plus 1 by adding 1 electron. And then I have to find the least common multiple between 2 and 1, which happens to be 2. So I multiply this reaction by 2. I add them together. I explicitly showed how the electrons cancel on either side. And I'm left with copper plus 2 nitrates plus 4 protons to give me copper 2 plus 2 moles of nitrogen dioxide plus water. Anybody seen this reaction before? Anybody remember the first lab in Gen Chem where you actually played with chemicals? Where you made that nice, funky brown smoke in the hood? That's the balanced chemical equation for the reaction of nitric acid with copper. It's a redox reaction. It's not an acid-base reaction. Okay, you're actually oxidizing the copper using the nitrate from nitric acid. Okay, so let's try basic conditions. Okay, basic conditions are only a little bit more difficult, and it's because we have to use one more step. Or at least if you use my procedure for balancing, you only have one more step. All right. According to your textbook, you have a whole new set of rules to follow. I think it's kind of stupid to remember 2 sets of rules, just remember 1. Okay? So, first, iodine plus permanganate to give me I2 plus manganese dioxide. We need to assign oxidation numbers to all the atoms as if on a substance being oxidized or reduced. Okay, well, iodide, that one's easy. It's just -1. Then we have permanganate. If you remember permanganate from the first example that I did today, permanganate is a +7. Okay. Now we don't necessarily need the oxidation numbers except to identify what's being oxidized and reduced. Iodine is going from -1. What's the oxidation state for iodine in I2?
0.
0. Okay, it's in its elemental form, so it's got to be 0. So I'm going from -1 to 0. Am I losing an electron or gaining an electron?
Gaining.
Losing, so it's going to be on my oxidation half reaction. Permanganate, if you remember from last time, in permanganate, manganese has a 7+ oxidation state, if you remember. If not, look at your notes. I did the calculation. Manganese dioxide. The oxygen, it's a dioxide compound. It's not a peroxide or a superoxide. Oxygen has to have a -2 charge oxidation number. There are 2 of them, meaning that my manganese here has a 4+ oxidation number. Okay? Alright, so that helps me to identify what's being oxidized and reduced. Iodide is being oxidized while manganese is being reduced. Being reduced from 7+ to 4+. Okay? So separated into 2 half reactions. Well, everything that contains iodide is going to be in my oxidized half reaction. So it's going to be I- going to I2. And then permanganate going to manganese dioxide is going to be my reduction half reaction. All right. The next rule, after I separate it into half reactions, the next step is to balance with respect to mass. Start with everything other than H and O first. Okay? Well, I have 1 iodide going to 2, so I'm going to need a 2 here in front of the iodide. 1 manganese going to another 1 manganese, so I don't have to do anything with the second reaction. Okay? So I put a 2 in front of the iodide, that balances the oxidation half reaction. I do nothing to the reduction half reaction. All right, so a lot of these steps, there will be nothing that you have to do. Okay. Balance the oxygens by adding water. Well, there are no oxygens in the first reaction, the oxidation half reaction. I'm done. Reduction half reaction, I have 4 oxygens on the reactant side. I only have 2 on the product side, meaning I need 2 more on the product side. So I'm going to add 2 waters. All right. Next step, balance any hydrogen by adding protons. I have no protons in the oxidation half reaction, so I do nothing. Reduction half reaction, I have 4 protons on the product side, meaning I'm going to need 4 protons on the reactant side. Okay, now here's the problem. We just balanced this in basic conditions. In basic conditions, I cannot have an excess of protons. This reaction right here, I have an excess of protons on my reactant side. That's due to the fact that I'm reacting this with concentrated nitric acid. This is what you guys did in lab. That's acidic conditions. This reaction is explicitly done in basic conditions. I cannot have excess protons. So what I'm going to have to do is I'm going to have to add enough hydroxide to neutralize those 4 hydroniums. And I'm going to have to add it to both sides. Because right now it's balanced. Perfectly balanced with respect to mass. If I add hydroxide to one side, what happens? My oxygen is now going to be unbalanced. So I have to add the hydroxide to both sides of my reaction. Okay, neutralize that excess hydronium by adding hydroxides. There was nothing to do on the first one. Second one, I have to add hydroxides to both sides. Okay, now, whenever I have hydroxide and hydronium in solution with one another, they react to give me water. It means this is going to produce 4 waters. Okay, I have to adjust for the created waters. This produces 4 waters, but I now have 4 waters on the reactant side, 2 on the product side. 2 of them are going to cancel. Okay? Cancel if necessary, and we're going to do so. And there is my balanced half reaction in basic conditions for the manganese. Yes, it's a couple of extra steps in there. Okay? But basically it makes the rules the same. I mean, you know acid-base chemistry. You've been tested over it twice. All right? Now I have to balance with respect to charge. Iodide is 2 times a minus 1 is a minus 1 on the reactant side, and a minus 1 on the product side. Since iodine is the oxidation half reaction, it's losing electrons, meaning I'm going to put the 2 electrons on the product side. In the reduction half reaction, I have a minus 1 on the reactant side, I have 4 minus on the product side. It's reduction, it's gaining electrons. I'm going to need to add 3 electrons to the reactant side. Okay. Now, charges are balanced, all my mass is balanced. Now all I have to do is balance the 2 half reactions with respect to one another. And I do that by making sure that my number of electrons in both half reactions are equal by finding the least common multiple. Do you have a question?
On the test, will we know if it's basic or not?
You'll be told. Balance the following redox reaction in either aqueous or in basic. We'll tell you one way or the other. Okay. So now we need to make sure the number of electrons, we need to balance the number of electrons by finding the least common multiple. Same rules as last time. All right, what's the least common multiple between 2 and 3? 6. So I'm going to multiply my oxidation half reaction by 3. I will multiply my reduction half reaction by 2. And then I'm going to add the 2 together after I pull the 3 all the way through and the 2 all the way through. So I'm going to get 6 iodides to give me 3 iodines plus 6 electrons. 6 electrons plus 4 waters plus 2 permanganate to give me 2 manganese dioxide plus 8 hydroxides. Add the 2 things together. 6 iodides, 4 waters, 2 manganese dioxides, 3 iodides, 2 manganese dioxides, and 8 hydroxides. Okay. Check to make sure it's balanced with respect to both mass and also charge. 6 iodines. 3 times 2 is 6. Okay, good. 4 times 2 is 8 hydrogens, 8 hydrogens. 4 times 1 is 4. 2 times 4 is 8. That's 12 oxygens. 2 times 2 is 4. Plus 8 is 12 oxygens. And that's balanced with respect to mass. Check charge. 6 times a minus 1 is a minus 6. 2 times a minus 1 is a minus 2. That's a minus 8. And then we have 8 hydroxides. So we have a minus 8 on both sides. Charges are balanced. Okay? All right. Do one on your own. Balance the following in basic. We have perchlorate. Sorry, that's not perchlorate. That's hypochlorite. Plus chrome 3 hydroxide going to chromate plus chloride. Same set of steps as before.
Yeah, orange is minus 1.
First step, figure out what's being oxidized and reduced. Give you a hint. I even told you what the oxidation numbers are. Split it into the 2 half reactions. One for oxidation, one for reduction. Balance with respect to mass by balancing everything but HNO first. Then balance O by adding water. Balance H by adding protons. Since we're in basic conditions, we have to neutralize all the excess H's by adding hydroxides to both sides. Making water, canceling water, balance electrons, add.
No idea what it's doing.
just gonna see, is it, well, does this look right? What I forgot to do is learn how to do assign.
Okay, so you do 4 times. Nothing mine times 4.
Oh, okay. But I don't even know the. So it's 4 times this whole thing, or this? We know.
I think it's the whole thing.
Whole thing. Okay, we'll figure it out. Okay, so what is being oxidized? Our choices are chlorine, chromium, oxygen, or hydrogen. What's being oxidized? What's losing electrons? Chromium. So my oxidation half reaction is going to be CrOH4 minus. I'm going to leave off the phases so we can write all this stuff out before we have to leave. Chromium, give me chromate. That is my oxidation half reaction. My reduction half reaction is the hypochlorite going to chloride. Okay? That's step number 1 and step number 2. Step number 3 is balance with respect to mass, but I have a series of steps on step 3. Step 3.1, 3.I, what do you want to call it, is balance with respect to everything but H and O. 1 chromium, I'm done. 1 chlorine, I'm done. Okay, fine. Now, I need to balance with respect to O. And I'm going to balance with respect to O by adding water. I have 4 oxygens here and 4 oxygens here. Hey, guess what? I'm done. But over here, I need to add 1 water. Okay? Now, next step is to balance H's by adding hydronium, or actually adding protons. I have 4 H's here, so I'm going to need to add 4 hydroniums here. I have 2 H's here, so I have to add 2 hydroniums here. All right, so now I'm balanced with respect to mass, except for the fact that I'm in basic conditions, meaning I cannot have excess hydronium. So what that requires me to do is neutralize the hydronium by adding hydroxide to both sides. So I'm going to pull this down to the next line so I don't run into that reaction. When I add hydroxides to both sides, this is going to give me OH minus plus CrOH4 minus, giving me chromate plus 4 waters. I did the same thing for the other side, add hydroxides to both sides in a sufficient amount to neutralize the hydronium. So 2 OH minuses, 2 OH minuses. This is going to give me 2 waters plus my hypochlorite, giving me chloride plus a water plus hydroxide. Now, One of these waters cancels. Leaving me with water plus hypochlorite to give me chloride plus hydroxide. Okay, so I'm balanced with respect to mass, now I need to balance with respect to charge. This is my oxidation half reaction, meaning I should add electrons to what?
Why did you only add one hydroxide?
You're right, I should have added 4. Because I added 4 waters, right? Thank you. Okay? Yes?
Doesn't mean you only added 2 hydroxides, but only one on the other side.
Correct now? Okay, I'm not using my cheat sheet. Okay, so now I'm finally balanced with respect to charge and mass. 4 minus 1 is a -5, -3. I need 3 more minuses, so I'm going to add 3 electrons. Over here I have -1, -1, -3. I need 2 more minuses over here, so I need to add 2 electrons to my reduction half reaction. So, putting all of this together, find the least common multiple. Between 2 and 3, the least common multiple is 6. So I have to multiply this half reaction by 2. So I'm going to have 8 hydroxide plus 2 chrome 3 hydroxides to give me 2 dichromates plus 8 waters plus 6 electrons. Multiplying this one through by 3, I get 6 electrons plus 3 hypochlorites to give me 3 chlorides plus 6 hydroxides. My 6 electrons on either side cancel. These 6 hydroxides cancel here, leaving me with 2. And I am left with 2 hydroxides plus 2 chrome 3 hydroxides plus 3 hypochlorites to give me 8 waters plus 2 dichromates plus 3 chlorides. Let's see if I got that right. What did I do wrong?
Not the water on there.
What did I do wrong?
Left the water on there.
Well, it just goes to prove I have to use my cheat sheet. We'll start there on Wednesday. Thank you for your time and attention.
I'm just gonna talk to him. How's the argument?